Okay, so let's get started here. We will continue in this data summary and analysis section. Then at 1:20, we will spend our extra class time going over the first assignment in more detail than I would normally in a classroom situation. Also, as a reminder, assignment number 1 is due on September 9th at noon. Are there any questions before we get going here? Okay, so this section focuses on a few different SAS procedures where the goal is for you to start understanding the I accidentally closed out my file where I had the lecture notes open. Okay, so again, the goal is to help you understand the syntax that is often very common from one procedure to the next. And so we looked at proc means. Now we're going to look at proc reg here. Reg stands for regression. So we're going to do some regression modeling here. And we're going to get back to the GPA data set that we've looked at previously. Just as a reminder, we have a response variable or dependent variable, symbolically we can call it Y, which denotes the college GPA of a student. And then X, which is our, you call it covariate, you call it independent variable, or you call it an explanatory variable, which is my preferred term because it's trying to explain information about Y. And this X is the high school GPA. And what we'd like to do is estimate a simple linear regression model that uses high school GPA to predict college GPA. And so the population regression model then is stated as shown here, where we have the expected value of Y. What would you expect Y to be on average? Set that equal to a Y-intercept parameter, beta 0, that we need to estimate, plus beta 1, which is another parameter that we need to estimate, and that's the slope coefficient on X, our high school GPA. So that is my regression model. That's my population regression model. You can say then with our data that we're going to use, we're going to come up with the estimated or sample regression model. It looks like that. Notice how we put hats on certain things to say, hey, we got estimated values. Y has a normal distribution where the variance is sigma squared. And again, we have 20 observations in our data set. So do note when I was looking over my lecture notes before class, the file that we are going to talk about here, gp_data summary.sas, I made some small revisions to it. So if you were getting a head start and downloading my files before today, I recommend re-download this file again because there are some small changes to it, basically just additions. Okay, so here's my program, and again, the first line, that's going to clear out my log and results viewer windows. I have some options of what I want the results viewer window to look like. I have some nice descriptive comments. I'm going to put my name at the top of every single page of that results window, results viewer window. My data that I'm going to use for this particular problem is a comma delimited data format. And again, there are two different ways that you can import these. One is proc import, and the second one is a data step. So just again to get you familiar with the very common ways that people get these data sets into SAS, I'm going to now use a data step rather than proc import as I did with the serial data. And so as a review, again, say data, and whatever you want to call the new data set. I'm going to call it set 1 for the lack of a better name. Where is my file? That's where you put that's what you state in the in-file statement. Then I have some additional options, such as my first observations in row 2, and I'm using a comma delimited file format. The variable names, in other words, what do I want to call each column? I'm going to call HS for high school, and then college for college GPA. I run it, and I print it off just to make sure that indeed it worked. And just from looking at it, yes, indeed, It does look like it worked, so that's good. I can also look in my log window as well to verify, yeah, that looks like things worked out good. Okay. Okay, next what I like to do is actually estimate the regression model. So here's the simplest way that you can use proc-reg to do this. First of all, I have a title to statement because now on the second line of every page in the output, on the results viewer, I want just some description of what we're doing here while we're estimating a model for the GPA data. So I say proc-reg, and as in every proc line, you usually have some kind of options. My option here says, well, what data set am I using? Set 1. And next, I need to specify what my model is. So in a variety of SAS procedures where you are doing some kind of modeling, you need to state your model, and so that's why there's a model statement. So I say model, I put my response variable first, equal, and then put my corresponding explanatory variables after it. So if I were to have, let's say, 2 explanatory variables, let's say I have ACT score as well, I would simply type ACT as well and separated the 2 variables with spaces. Then I say run to go ahead and go do it, SAS. And let's see what happens. So I click on the little running person symbol, submits it. And notice how SAS is thinking here. It takes a while for the results to actually be printed to our screen. I'll discuss more about why that's happening shortly. It's not like we're doing complex calculations here, so you wouldn't expect it to be so long. So here's my corresponding output that I get. And, you know, I would expect that all of you should have all estimated regression models in the past, so you may or may not have done it in SAS, but still a lot of the stuff in this output should look familiar to you. Let me actually go over to my notes so I can annotate on this rather easily. So this is on page 9. So obviously my sample size is 20. Now notice here it says number of observations read, number of observations used. Hopefully they match. If they don't, what that basically says, okay, SAS for some reason is not using all the observations. That often occurs, for example, when you have missing data. And if you're unsure if you read in your data correctly, you know, maybe you're concerned that maybe SAS wasn't able to pick up some stuff in that data set, you know, it might actually put a missing data value in for maybe like an X. And I think I mentioned this last time, correct me if I'm wrong, but often SAS, well, I shouldn't say often, SAS uses just a plain old period in your data set for a particular value that's missing. And so if I had 19 observations that had an actual X value and 1 observation that had a period there, you would see the number of observations used was 19 with this procedure. Then we have an analysis of variance table that tells me some information about my model. We have an R squared. Could someone tell me what that's saying to us? I would expect all of you probably seen R squares before.
How well the line fits the data.
How well the line fits the data. So an R squared is often referred to as a coefficient of determination. It's between 0 and 1. The closer the 1, the better it's to fitting the model. Or the better or the closer the points are to the actual regression line. We want this R squared to be as close to 1 as possible. Then we have some other information. We have a parameter estimates table, and what this now is giving me information so that I can actually write out my sample or estimated regression model. So I could begin with y hat is equal to, what do you think the intercept term is? Yep, 1.0, oh, we'll just say 1.09, I'll do some rounding. Plus, what's the slope? 0.61 times x. So I can say where x is equal to high school GPA if it wasn't already defined, y is college GPA. So that will be a proper way to write out an estimated regression model. Another way you could do something like this is you could say college hat is equal to 1.09 plus 0.61 times high school. That would be another proper way to do it. That's kind of a, not as formal, but it gets the point across. Now, would it make sense to write out your model like this? Y is equal to 1.09 plus 0.61 times x. No, because we are using this model to predict y. This says, okay, the true value of y is, well, that's great if you knew that, but you're not going to know that in an application. So that is not a proper way to write out your model. So we also have a column here. So notice where we got this from. So we have a parameter estimate column. We have some information here on the rows that tells us what part of the model this corresponds to. We also have a standard error column. So this right here is the square root of the estimated variance of beta hat 1. Again, the square root of the estimated variance of beta hat 1. That's what standard errors are, just a different name. You could say also the estimated standard deviation of the statistic. That's what a standard error is, just a different terminology. So we also have a column called t-value. What do you think this 4.95 is doing? Or how do you think it was found? Beta hat 1 divided by the standard error. Why do you think that's important to do? To perform a hypothesis test. Yes. This is what the hypothesis test is. Is beta 1 equal to 0 or not? So if beta 1 is equal to 0, what does that say for us? It says that high school GPA is not linearly related to college GPA. So we're performing a hypothesis test here to say, hey, is high school GPA important, at least in a linear sense? So what do you think the next column is going to give you then? The p-value, exactly. So you notice it says PR greater absolute value of t. Well, how do you find a p-value in this situation? Well, it's 2 times the probability that a random variable t with a distribution of a random variable t that has a t distribution with 18 degrees of freedom is greater than the absolute value of 4.95. So PR, sometimes instead of using like a capital P to mean probability, some people use a capital P and an R. That's why you see that there. And I have the 2 out in front there because it's going to be a 2-tailed test. Notice how in the alternative hypothesis how I have a not equal to there. And so anyway, so I have a p-value. So given that p-value, would you reject or not reject HO? Reject, yeah. P-value is extremely small. So we could say something like this is a formal conclusion. Because the p-value is very small, there is sufficient evidence to indicate that there's a linear relationship between high school and college GPA. Suppose the p-value was 0.5. Would you reject or don't reject HO? You don't reject. Now let's be careful about how you word that conclusion. Here's an incorrect conclusion. Again, incorrect. There is no linear relation. Sorry, let me reset. This is incorrect. There is no linear relationship between X and Y. That's incorrect. Because in order to do a hypothesis test, and you'll learn this more, the more mathematical details in Stat 883, you have to, again, make the assumption that the null hypothesis is true first. And you're looking for evidence to, reject that null hypothesis. And in order to do the actual calculations itself, if you actually look at, and you'll see this at some point in another class, when you actually look at that t-test statistic, how it's formed, you're basically putting the 0 in there for that null hypothesis in the numerator of the test statistic. Now, the correct way to phrase then this conclusion would be to say something like this. There is not sufficient evidence to indicate a linear relationship exists. And you have to be very careful on that terminology or wording. I don't say a linear relationship does not exist. I just say from our data, we cannot prove the null hypothesis to be incorrect. So I'm leaving it open. It may be incorrect, or it may be correct. I just don't know. This also comes down to, and again, for beginning stat students, this can be a difficult concept. It all comes down to this. The probability of a type 2 error. Do you control the probability of a type 2 error when you do hypothesis testing? What do you control? Probability of a type 1 error. What is a type 1 error? Just to review. You reject HO, but HO is true. Oftentimes we control that with a probability of 5%, alpha 0.05. But you never see anybody ever state, what's the probability of a type 2 error? Often referred to as beta, symbolically, which is different from the betas in our model. I know that can be kind of confusing. But you don't control that. And so if you don't control that, and the type 2 error would be your probability you don't reject HO, but HA was actually true. You don't control that, making that kind of a mistake. So you have to be very careful on how you word this kind of stuff. So now also with my output, I got a bunch of plots. I have a bunch of diagnostic plots to look at, for example, are there outliers? Are my assumptions of normality at least reasonably satisfied? Don't worry about this plot. I assume that in study 21 you'll be talking about diagnostics, and I think it's good enough just to leave it to that. You also have a residual plot. This is where you often look for outliers or, again, trends. If there were trends in this plot, this would indicate that your explanatory variable is misspecified in your model. So, for example, if you were to see some kind of quadratic trend there, that often indicates that maybe you need like a high school square term in your model. If you want to know more about that now, before you get to like an 821, take a look at my Stat 870 notes online. But the plot that you're responsible for is this one right here. This is a common plot that you see with simple linear regression. So on the y-axis you have your response, college GPA. On the x-axis you have your explanatory variable, high school GPA. The open circles are the actual plotting points. I'm sorry, the actual observations in your data set. They are plotting points. The dark blue line is your y hat, and I'm not going to specify the exact model. I'll just put it in symbolic terms there. So that's your estimated regression model. The blue colored in area there is representing 95% confidence interval bands for the expected value of y. So, for example, let's say that x was 3.0. If I were to go up to that blue colored band there, if I could go up straight, sorry, I'm not the best drawer in the world here, and if I were to hit the bottom of it and then project, project over, imagine that it is a straight line over. what that would say, and that's probably about 2.6 maybe, my lower bound in that confidence interval for the expected value of y is 2.6. The upper bound is about, we'll say 3.05. I am 95% confident that if high school GPA was 2.6, my expected value of y, expected college GPA, be somewhere between 2.6 and 3.05. So again, that's for an x equal 3.0. So that's how you can use that plot. You can do a similar thing for x equal 3.5 or 3.2. It doesn't matter. But that's how you use the plot. Now, if you've each confidence interval that you form with that is 95%, has a 95% level. So this is if you've heard of individual confidence levels, this is an individual confidence level. This is not a family-wise confidence level, meaning that every possible one has a 95% confidence level. The actual confidence level for the entire band is actually going to be something less than that. I'm not going to test you on that, but I just thought I'd mention that because you should see this in other courses too. Now the blue dotted lines, those are prediction interval bands. So for example here, the bottom value of that, or bottom bound for that prediction interval at x equals 3.0 is about 2. The upper one is about 3.5. Could someone tell me the difference between what that prediction interval will do versus a confidence interval in this situation?
Is the prediction interval, like for any given point, there's a 95% chance of it being between there, and the confidence interval is that the true mean is between those 2 points?
Yes, I think you're getting at it. So a prediction interval is for a random variable, y. So in this particular setting, the differences between these two intervals is that y could be, let's say, for one student. The expected value of y is, on average, for all students with a GPA of 3.0, high school GPA of 3.0, this is what the mean GPA will be for college. So that's the difference between the two. It's a lot harder to capture an individual than a mean, and so that's an intuitive reason why the prediction interval is wider. Okay, so this can be a nice plot to look at. Now you might remember when I first ran Proc Reg, we can see that things were going kind of slow. It took a while to generate the output. Why? It's because of the plots. I think this is, to be honest, kind of poor that it takes SAS so long to produce these plots, but that's what it does. And so you might be thinking, well, can I tell SAS not to produce those plots? Yes, you can. Here's how. And I'm actually going to, it's actually on page 15. There are two main ways to do it. I'm going to show you the second way that I have in my notes first. And simply, there is an option on the Proc Reg line called plots. There's a variety of different values you can give plots. In this particular case, none produces the same output almost instantaneously, but without the plots. I find that to be helpful. I remember the first time that SAS added the feature, or at least the first time I saw that SAS had added this feature of this plots option. I didn't know about it. I ran my code, and I thought, is there a problem with SAS? Because it was just seemed like forever. It was for a larger data set, so that's why it was even taking longer to do the plots. And I thought something was going wrong. Eventually I figured it out, but I just wanted to warn you about that so you don't run into the same problems as I did. A second way to do it, and I'm not going to go over this in class, and this is what's actually indicated on page 12, is to use a statement called ODS. This will make more sense later on in the notes when we talk about the output delivery system. In the end, if I would rewrite my notes, I would have not shown that one until later in the notes. Okay. Are there any questions? So, how did I know about this plots option? Well, that's where the help comes in once again. No, I guess I could I have it in my notes, so just go in the notes. So here's the syntax for proc reg. Again, think of the similarities to what we've seen, like for example with proc means last time. So to begin with, again, we have a proc reg line, and notice it says options right after it. So if I click on proc reg, that's going to take me to all the options. One of the options that you will see is the plots option. This is on the next page right there. Okay? So if I click on plots, I'll see the variety of options that are available to me. You can tell SAS, hey, I only want one of the plots produced. Or as we did here, I don't want any plots. So there's a variety of different options. And this is where you as a graduate student can, after class, do some further investigations. Actually do this when you're walking through my notes, and then try out some of the options and see what happens. That's a great way to learn. Okay. Also, you'll notice here again is that data option. Back to the syntax here. So we see model. We used that statement before. Notice how it organizes this, the dependent variables, and what it calls the regressor. So another word for independent variable, covariate or explanatory variable. Too bad we just don't have the same terminology to mean one thing. And we saw this a little bit last time. In many SAS statements, you can do some additional options. And the way you access those options is do a slash and then put the options there. I'll give you some examples of that shortly. I don't use this very often here, but proc reg gives you a way that, let's say that you wanted to estimate a regression model for a college GPA and high school GPA, like we just did. But also using the same invocation of proc reg, you also want to do, let's say, college GPA and ACT score. So you want to have two model statements. And a way to label them nicely in the output then is to include a label. So, like model 1, model 2, And so that's what the label thing means. You'll see examples of that coming up. We have the by statement as well. Can someone tell me what by does again in terms of what we did with proc means? Excuse me? It doesn't sort, but you have to sort first before you use it. What? Let's say we had another variable in the data set. Let's call it university. Maybe we have data from a number of universities, and we want to fit models to the data from first university, the second university, to the third university, and so on. You want models for each. That's where the by statement can come in. And in order to use it first, you have to sort the data by the variable that you're using then for the by statement of proc reg. We also have a var statement. We've seen var before as well. To be honest, I've never even used this in proc reg before. It's not very useful in this particular case because when you specify the variables that you're using up here, that's all you need to do. You don't need to actually specify the variables there. It has a weird thing that it can do if you also specify it there. It's not important. We also have an output statement. What does that do? It allows you to create a new data set from this procedure that puts some of the calculations into it. Notice the syntax that like we saw in proc means. Out equal, you create a new data set name here. and then you have keywords, just like what we had in proc means, that specify what you want to put in this new data set. Okay. Obviously, there's a lot of things listed there. It's not important to talk about them all. Okay, let's see here. Let's actually take a look at an example. Yep. So this is on page 17 now. Okay, so let's put some of this stuff to use, these options. So I'm going to, at the bottom of page 17, you're going to see using proc reg again. So proc reg, first option, data equals set 1. And then another option I'm going to set, out s equal out underscore set 1. Well, what does that do? Well, this is where coming back to that help is helpful. So notice it's listed actually as the second option. It doesn't matter what order you put the options in on the same line. Out s equal outputs a data set that contains the parameter estimates. Okay, what this is going to do is create a data set that contains my beta hat 0 and my beta hat 1. Maybe for some reason, for some future calculations, I needed that information. Then alpha. Okay, you might be thinking, oh, we're going to do some kind of inference here. And in fact, this is going to be used for confidence intervals. So I'm going to have 95% confidence interval since alpha is being set to 0.05. And of course, I set plots equal none. I begin my proc reg, or the model statement here, which just shows you, hey, here's a label, my model, colon. Oh, that's so descriptive, as opposed to your model. Model college equal HS. I have a slash for some options. What do you think out SEB means? So out means something's getting out of SAS. But SE and then B, what do you think? Now, obviously, SAS is going to try to use names that, generally speaking, make sense for some reason. The abbreviation would make sense. What do you think? SE? Standard error. Yeah, standard error. And then B, instead of betas, they have a B there. Because some textbooks will use like B0 and B1 to mean beta hat 0 and beta hat 1. So what's going to happen is that the corresponding standard errors, that square root of the estimated variance of a beta hat, is also going to be put into out underscore set 1. Then we have CLM. What do you think that stands for? Confidence limit. What do you think the M mean? Okay. What does that mean here? The confidence limit for expected value of Y, because that's like a mean. What do you think P stands for? Excuse me? Good guess, but unfortunately it is incorrect, but thank you for guessing. P, I'm trying to predict something. Ah, these are going to be my Y hats, my predictions. So let's go ahead and run this and see what happens. So look at my output here. Notice at the top it says model, colon, my model. There's my label. It's big results from it. Second page now, we have a second page of my output. This is again for my model. And here you have a listing of all your all your Y's, your observed Y's in the order that they were in the data set. So the first student had a college GPA of 3.1. Then we have the corresponding predicted value. Let me go to my notes here so I can write on it nicely. Then predicted value, there's a Y hat. standard error mean predict. That is the square root, excuse me, the estimated variance of y hat for every observation. Then we have the confidence interval. So 0.278 is less than the expected value. Eraser out. Expected value of y is less than 3.11. So for the first observation, which has an x of 3.04, here's my 95% confidence interval for the expected value of y. And then the last column is residual. In other words, y minus y hat. So if I were to take 3.1 minus 2.9489, I get 0.1511. So that's all these extra options, this is what it gave me. Also what it gave me was, remember that data set that I asked for. So if I do a simple proc print on that data set, here you can see, if I look under the row 1 here, you see my beta hat 0 and the beta hat 1 lined up with the corresponding column. You also see, remember that option that we had, out SEB? Notice SEB there, here are my square root of the estimated variances for the corresponding statistics. Now, oftentimes you're faced with a situation where you're not for sure maybe exactly how this calculation was done. You want to maybe verify that indeed you got everything right. And so what you might want to do is actually verify how to this calculation by hand, so to speak. Meaning that let's actually program in the corresponding equation into SAS. And does anyone know or remember off the top of your head what is the equation that would be needed for this confidence interval? What do you think it begins with? Y hat. Y hat plus or minus what? A value for your t distribution, then 1 minus alpha divided by 2 quantile with n minus 2 degrees of freedom. Yep, the standard error. And I'll just say the square root of the estimated variance of y hat. If you want to know what goes in that formula, take a look at my Stat 70 notes. It's in chapter 2. So we know what y hat is. It's 2.95 about. I take plus or minus alpha's 0.05. So roughly speaking, this t distribution value is going to be about 2 point something. Times then, I also have that standard error, 0.0788. If you do the math, you will get that interval. Well, how can we have SAS do that quick little calculation for us, rather than maybe us taking out a calculator? Because after all, who actually uses calculators anymore? Here is what I added to my lecture notes right before class today, or not to my lecture notes, but to my program is, I show you how in a simple data step, how you can do some simple math. I decided to call the new data set that's going to contain my results, decided to call it temp. I simply type out my standard error. I type out my y hat. What about my t distribution value? Now this is new. I'm actually going to go over this more in detail later in the semester, but there's a function in SAS called quantile. I want a quantile from a t distribution, specifically the 0.975 quantile, with 18 degrees of freedom. Then, define my lower limit, take y hat minus that t value times SE. So notice what you can do. Since I already have values for these guys there, and this is where order does matter, I can now do a calculation here. And I can do a similar thing for the upper bound. So how about we run this and print it. And That is exactly what SAS gave us from ProcReg. So I think it's just a good illustrative tool how you can use SAS to do some of these calculations essentially kind of by hand to verify stuff. Any questions?
When we do our assignment, that part kind of by hand, can we program the equations in, or do you want to?
You can program the equations in like this if you want to.
Okay.
That's fine. It's just often when I say do stuff by hand, I don't want you to rely on, let's say, ProcReg to get that automatically calculated for you. I want you to show me that, yeah, you can do some of the calculations. I think you're talking about the t-test part, right?
Yeah.
Yeah. Okay. Now, notice, let me run ProcReg again here. I don't know if you've noticed this yet when using SAS, but whenever you run a procedure, you'll have information at the top saying, hey, ProcReg is running, or ProcMeans is running. And there are some procedures where that doesn't go away when you think, hey, it should be done. And the reason why that's important in this particular case is any kind of data set that I'm trying to produce or create with ProcReg will not be created until ProcReg stops running. So in order to have out_set1 to be actually created, I need to somehow tell SAS, stop. I'm done with ProcReg. Let's move on. How can you do that? Well, you could do a data step. You could run another proc, and then that will go away. So for example, it went away. Another way to do that is that you can actually issue a command called quit. So let me run all this. And you will see ProcReg went away. I think it's kind of just an annoying feature that some of these procedures are like that. That in order to get that data set to be produced, you need to actually say, stop running. Okay, so that takes us next to page 21, the output delivery system. So software packages that, or programming languages that have been around for a while, often will have multiple ways to do the exact same, essentially the exact same thing. Because, you know, people will think, oh, the current way is not sufficient if I want to do a particular thing. So let's create a whole new system to do it. And you're going to see this a number of times in SAS. I know from a teaching standpoint, it's like, okay, do I teach all the ways? Do I just focus on one? And it's been kind of a difficult decision for me at times. Because, you know, I learned maybe one way, I still use that, but now there's this new way that's better, but some people still use the old way, and you need to know both. So anyway, the output statement that we've seen with ProcReg and ProcMeans allows you to get information that a procedure is calculated out of the procedure and into a data set. Here's another way to do that with the output delivery system, or ODS for short. This came about SAS version 8. Right now we're at SAS version 9.4. And basically, some people who use SAS were having problems extracting exactly what they wanted that they could see in the output, but they just couldn't put into a data set. So SAS came up with this way of thinking about your output as every part of your output is a table. And that table can be put into a data set. Well, to see, well, what tables are available to us, there are a few different ways to do that. Method number one, this is with the, I'm going to switch back over to the serial data. So if you remember with the serial data, we had sugar, fat, and sodium as our three main variables that we were looking at. Let's say I want to find simply the means for those three different variables. And I want those means to go out of ProcMeans into a new data set. So I can save it and maybe do some calculations on it later. To see what the table name that you need to specify to get that information out, you can use ODS trace on. And what that's going to do is in your log window, it's going to tell you all the table names that are available to you that you can use to create a new data set with some of the results. So I'm going to say ODS trace on, and then I'm going to do trace off, so that anything between there is going to be traced in the log window. Oops. Let me actually read in the data set again. So you can see there's my output. Notice I got the means. And now look at the log window. We had the same things as we've seen before, but now we have output added. The name of this table is called summary. That's going to be then the keyword that we're going to use with a new ODS statement that will get the information out of SAS. Okay. Oops. And this is how you do it. So exact same code as before, but now I put an ODS statement inside of proc means. ODS, and I want to output some stuff. The keyword or that table name called summary, and then what I have after the equal sign is whatever I want to call the data set in SAS. So go ahead and run that. If I come over here to the Explorer window, I see something called ODS set 1. And there is that same information that we had seen printed, structured in a different way, yes, but it's at least available to you in a data set. Here's a key point. You can only put stuff that's in, only put stuff into a data set using ODS if you see the corresponding calculation done in your results viewer. So, for example, you're not going to see a standard deviation in that data file because I didn't calculate it. So that's a key aspect. Now, proc means is quite simple. You know, in terms of I think there's maybe just one table name that's available to you. With proc reg, there's a lot more available to you, and you could, you can still do. Find that. Let me just copy and paste this because it's a slightly different topic. So if I use that same ODS trace on and off and highlight that with the GPA data set, my data set disappeared. Sorry. Here you can see all the tables that are available to me. So for example, you might remember at the top of the output for the results viewer, you have the number of observations. There's a table for that. The ANOVA table, there's a table for that. Fit statistics, that contains, for example, R squared, there's a table for that. Parameter estimates, there's a table for that. So on your own, fool around with that and see what information is given out to you. Take a look at the data sets. Let me get to a good stopping point here, and then we'll start talking about the assignment. And the more options you set in a particular procedure, the more tables that you'll have available to you because there's more output that's available to you in the results viewer. So it's good to look at the SAS Help to figure out, well, what tables are available. And where the help is for ODS for a particular procedure is not necessarily in an intuitive spot. So for example, let's say I'm looking at the help for proc reg. If you look under details, then at the bottom you will see something called ODS table names. Every procedure's help is structured this way. So this is where you find the table names. You can also have SAS label the tables in the actual output itself. Meaning, if I come over here to the results viewer, oops. So you might expect, if you see where my mouse is here, might be, would be nice if SAS says, okay, this is the NOBS table. This is the ANOVA table. This is the fit statistics table, actually labeled in the output. SAS, for some reason, does not do this in the results viewer. But you can have SAS label it in the output window. So you may remember on the, I think it was the first day of class, where I actually talked about this output window. You see where my mouse is. Here's how I get to the output window. This used to be, before version 9.3 of SAS, this used to be where all the output would go by default. It would not go to the results viewer window. It would go to the output window. And if you redirect procreg's output or any procedure's output to the output window, you can tell SAS, hey, print the table name right next to the output. I don't know why SAS didn't extend that over to the results viewer, but it hasn't. So how can you tell SAS to redirect the output to the output window? You say ODS listing. Well, why doesn't it say ODS output? Well, it's just the terminology that SAS has used. Previously, the output, they often refer to as a listing of the output. That's where the name comes from. And then you use the exact same code as before, ODS trace on, but now you have a slash an option. Put that trace now into the listing or that output window. Then I run the same SAS code as before. I turn off the tracing, and I don't want to print any more stuff to that output window. So let's run that. You can see what happens. So let me back up here. So you can see how, just like in that log window, you see the same kind of syntax about how stuff is labeled in terms of the tables. And when I first started using ODS, this is what I did all the time when I wanted to see what the table names were. I think it's still useful. Okay. Just a little bit more. Sorry. Also, let me go back to the results viewer. Another way to figure out what those table names are, and this is on page 28, is remember over here in the results window, I said the first or second day of class that basically what this provides is a hyperlink, you could think of, to where output is located in the results viewer. So if I were to come over here and click on print, and then the corresponding thing below it, it takes me to that part of the results viewer where that's located. But also what this provides you, if I go down here to procreg, so procreg model 1, that's the default label, the fit of the model, and there's just so many ways to click. Eventually you'll get to what looks like a Internet Explorer icon. Remember, everything in the results viewer is actually an HTML web page. I mentioned that once before. It's okay if you didn't remember that. But if I right-click on this, bring up Properties, notice how it says HTML, but it also gives a table name and ops, for example. And then this right here, the URL, what it says, this is the actual physical place on your hard drive where this results viewer HTML file is located. When you close out SAS, that automatically gets deleted. But that's the physical place. You can actually go find it on your hard drive. And there was a few small things that I skipped over. I kind of addressed, but maybe not as fully as I want to. Make sure you take a look at the notes, and then that's going to take us up to page 29. And next time when we go over the notes, we'll talk about starting on page 29. But what I want to do next now is take a look at assignment number 1, problem 2. Okay. So problem number 2 is going to give you some experience with using ProcReg. And the example that I chose for this involves what's called stability testing. Let me get my prop out. So whenever you buy some kind of pharmaceutical drug, this is simply the Advil that I have in my office sometimes when students give me a headache. Anyway, whenever you buy some kind of pharmaceutical product, there will be an expiration date on it. And interesting, when I was going through my lecture notes this morning before class, I noticed the expiration date here is June 2016. So obviously I need to replace this. But this is the expiration date, meaning that you shouldn't take it anymore after June 2016. How do pharmaceutical companies figure out what that expiration date is? They use regression models, essentially. And the whole process of determining that expiration date is called stability testing. They want to know how stable a drug is over time. And so what they'll do is, like, we'll take the case of this Advil here. Imagine that, I can't think of the company's name that makes Advil, but they have a batch of these Advil tablets. And they're going to take a few of them out of that batch, and they're going to put them into storage in their facility. Then at maybe like time equal 3 months, time equals 6 months, time equal 9 months, a person's going to go into that storage place, they take out a tablet, and they perform some measurements on it. They might do simple measurements such as the color. Has the color of the tablet degraded over time? And from a marketing perspective, Advil tablets are brown. If it had turned yellow for some reason, a customer might not like that. So they don't want customers to have tablets that are yellow. But it might be some other safety things. It might, and the one that you're going to focus on is the potency. The potency. How strong is that drug? And every pharmaceutical company is required to state how strong a particular drug is. And the FDA, the Food and Drug Administration, requires that the potency be at least 95% of what is stated. If it goes below that, can't let consumers have it. So what pharmaceutical companies do is that they use time as an explanatory variable, and then the response would be, in this case, potency. They fit a simple linear regression model to it, and based upon that model, where basically you could, and it's a little bit more complicated than this, but where it hits 95% potency, that's then the corresponding time is the shelf life. How long a pharmaceutical drug can be on the, let's say, the shelf at a grocery store before it has to be taken off because it's not as potent as it should be. So let's say the shelf life for these pills were like 9 months. If the drug was manufactured, let's say in January 1st of this year, then that would mean the expiration date would be September. So that's how the shelf life and expiration date go together. So here's some data. This isn't real data. Some data that I want you to examine for this particular assignment with the stability testing in mind. So at time 3 months, the potency of, let's say, the tablet was 101%. You note that there was a slight typo in the actual assignment, I believe. So it's 101.55%. So part A, use a data step with the data line statement to get the data into SAS. What that means is that you, and we looked at one example like this before, you can actually type in your data into SAS rather than reading in from an external file. So I want you to type it in SAS, with inside a data step, use a data line statement, get the data into SAS, print it off. Part B, well, go ahead and estimate that regression model using time as the explanatory variable, potency as the response. Use procreg to do this. Actually state the regression model. So you're going to have potency hat is equal to whatever beta hat 0 is plus beta hat 1 times time. Interpret the relationship between time and potency. Meaning, is there a negative relationship, positive relationship, or is there no relationship? Based upon what you see for that beta hat 1, that's going to lead you to a conclusion. Part C, is there sufficient evidence to indicate a linear relationship between time and potency? Use the appropriate statistical inference methods to make this judgment. So what do you think you're going to do? You're going to do a hypothesis test, okay, similar to what we did in class. Part D, use procreg again. And I failed to mention in Part B, I didn't want to see any plots. But in Part D, I do want to see some plots, or one plot, only one plot. And I want to see that plot that has the estimated regression model on it, the data plotted, the confidence interval bands, and the prediction interval bands. I want to see that plot and that plot alone of all the plots. So what that's going to mean is you're going to have to dig into the help for the plots option and figure out what's the correct option or what's the correct value for plots to specify I only want this one plot. And then lastly, part E is I want you to figure out what the shelf life should be for this drug using the method that the FDA uses. Okay, let's talk about that. So you're going to have a plot from the previous part that has time, has potency, and you're going to have some data points, and I'll give you a hint, they will be going downward. And you're going to have the estimated regression model going through the middle of those points. Again, that should be a straight line. Well, let's get a different color here to make it look nicer. We'll use blue. And you're going to have some confidence interval bands. And I'm just going to leave off the prediction interval bands for now. I'm just going to move on. Now, what the FDA says, again, that you need to have the potency remain above 95%. So let's put a line here at 0.95. Now, I haven't shown you yet how to put a 0.95 line there, so don't worry about it. But imagine there's a 0.95 line there. I mean, when you, let's say, copy and paste your stuff into, let's say, Word, you could, use one of Word's tools to, draw a little line on there. But the FDA says, okay, the shelf life then is the time point where this 0.95 line hits the lower confidence interval band. So in this case, if I project down, whatever that time is, that's the shelf life. And that's how people actually do this in the pharmaceutical industry. I should say it's a little bit more complicated, but essentially this is how it's done. So I want you to do that and tell me what the shelf life should be for this particular problem. Obviously, you're going to have to approximate it because you're just kind of eyeballing it. For other assignments, we'll look at more, let's say, sophisticated methods that you can use to come up with a more exact value. Okay. So are there any questions about that? Okay. Then that's all I have for today. Again, if you have any questions about the assignment, please feel free to post them to the listserv. Again, this is due September 9th. So that's it for today.